Lesson: Deep Learning Foundations. Deep learning has revolutionized the field of artificial intelligence, enabling machines to achieve human-like performance in tasks such as image recognition, natural language processing, and autonomous driving. At the core of deep learning are artificial neural networks, specifically designed to mimic the human brain's ability to learn from data. This lesson will delve into the foundations of deep learning, focusing on advanced neural network architectures and their practical applications. It will provide actionable insights and tools for professionals aspiring to become certified AI implementation professionals. Artificial neural networks are computational models inspired by biological neural networks. They consist of interconnected nodes, or neurons, organized into layers. The power of deep learning lies in its ability to automatically learn hierarchical representations of data through these layers. This capability is particularly evident in convolutional neural networks, which excel in processing grid-like data such as images. CNNs employ convolutional layers that scan input data with filters, capturing spatial hierarchies and patterns. This makes them ideal for image classification tasks. For instance, Google's Inception network achieved top performance in the ImageNet Large-Scale Visual Recognition Challenge by employing a complex architecture of stacked convolutional layers. Recurrent neural networks are another crucial deep learning architecture, particularly suited for sequence data. Traditional RNNs suffer from the vanishing gradient problem, which hampers their ability to learn long-term dependencies. Long short-term memory networks, a variant of RNNs, address this issue through specialized gating mechanisms that allow them to retain information over extended time periods. LSTMs have been pivotal in advancing natural language processing, as demonstrated by Google's use of LSTMs in their language translation services, significantly improving translation accuracy. The development and deployment of deep learning models require robust frameworks that streamline the process. TensorFlow, an open-source framework developed by Google, has become a cornerstone of deep learning applications. TensorFlow provides a comprehensive platform for designing, training, and deploying neural networks at scale. Its flexibility and scalability make it a preferred choice for industry professionals. PyTorch, developed by Facebook, is another popular framework known for its dynamic computation graph, which allows for more intuitive model design and debugging. Both TensorFlow and PyTorch offer extensive libraries and pre-trained models, enabling practitioners to tackle real-world challenges efficiently. Transfer learning is a powerful technique that leverages pre-trained models to solve new related tasks with limited data. It addresses the common challenge of data scarcity by fine-tuning existing models on specific datasets. For example, a pre-trained CNN on ImageNet can be adapted for medical image classification with far fewer labeled samples. Transfer learning not only reduces computational costs, but also accelerates model convergence, making it a valuable tool in practical applications. The impact of transfer learning is evident in the medical domain, where it has enhanced diagnostic accuracy in detecting diseases from medical images. Despite the advances in deep learning, interpretability and explainability remain critical concerns, particularly in high-stakes applications such as healthcare and finance. Model interpretability ensures that AI systems can be trusted and understood by human users. Techniques such as feature visualization and SHAP provide insights into how neural networks make decisions. SHAP, for instance, offers a unified measure of feature importance, allowing practitioners to understand the contribution of each input feature to the model's predictions. These tools are essential for building transparent AI systems and fostering user trust. Automation in model training and hyperparameter tuning has gained traction with the advent of AutoML. AutoML frameworks like Google's AutoML and Microsoft Azure's Automated ML simplify the process of selecting optimal architectures and hyperparameters for specific tasks. This automation not only accelerates the development cycle, but also democratizes access to deep learning by reducing the need for extensive expertise. AutoML has shown promise in diverse applications, from optimizing recommendation systems to improving customer engagement in e-commerce. Ethical considerations are paramount in deploying deep learning models, as biased algorithms can perpetuate injustices in society. Ensuring fairness and mitigating bias in AI systems require careful dataset curation and algorithmic checks. Techniques such as adversarial debiasing and fairness constraints are employed to address bias in model predictions. These methodologies are particularly relevant in hiring practices and credit scoring, where biased decisions can have significant societal impacts. Ethical AI development is not just a technical challenge, but a societal imperative that demands concerted efforts from developers, policymakers, and stakeholders. The scalability of deep learning models is a critical factor in their deployment in real-world applications. Distributed training techniques enable the parallelization of model training across multiple GPUs or machines, significantly reducing training time. Frameworks like Horovod, built on top of TensorFlow and PyTorch, facilitate seamless distributed training, making it feasible to train large models on vast datasets. The scalability of these models is evident in applications like speech recognition, where large-scale datasets are essential for achieving high accuracy. Deep reinforcement learning, a subset of deep learning, has opened new avenues in decision-making problems. By combining reinforcement learning with deep neural networks, agents can learn complex strategies in environments with high-dimensional state spaces. AlphaGo, developed by DeepMind, exemplifies the success of deep reinforcement learning, defeating the world champion in the game of Go, a task previously thought to be beyond the reach of AI. The principles of deep reinforcement learning are being applied in diverse fields, including robotics, where it enables robots to learn tasks through interaction with their environment. In conclusion, deep learning foundations form the bedrock of modern AI applications, offering unparalleled capabilities in processing and understanding complex data. Advanced neural network architectures like CNNs and LSTMs have revolutionized fields such as computer vision and natural language processing. Frameworks such as TensorFlow and PyTorch provide the necessary tools for developing scalable and efficient models. Techniques like transfer learning and AutoML streamline the deployment process, while interpretability and ethical considerations ensure responsible AI development. As deep learning continues to evolve, its applications will expand further, empowering professionals to tackle increasingly complex challenges and drive innovation across industries.